Laplace expansion of determinants. In this video, we shall provide a direct proof of this result. Let us quickly recall the definition of determinants. To find determinant, we start with a square matrix, and then we take one entry from each row and each column. Suppose I start with this fellow. The moment I take this, I am not allowed to take anything in that row or anything in that column. And then I have to pick something which is not selected, anything. Suppose I take this. Then again I have to strike out everything in its row and everything in its column. And that leaves me only one entry in this case because it's a 3 by 3 matrix. I select that. Then I will multiply all my selected numbers. Now the way I did this was quite arbitrary. I could have started with something else and proceeded in a different way. It is not very difficult to see that each such choice actually corresponds to one permutation of 1 to 3. To understand this, suppose I list all my rows 1 to 3 and all my columns 1 to 3. Now when I picked this fellow, I picked row 2, column 1. It is like mapping 2 to 1. So I will draw an arrow from 2 to 1. And then I am not going to use 2 and 1 anymore because I have struck them out. Then I chose this, which is in row 1, column 3. So 1 goes to 3. And that left me only other choice, 3, 2. So I joined it like this. So this is what is called a function, in fact a bijection from 1 to 3 to 1 to 3. That is a permutation. So I can express the same thing instead of drawing such arrow diagrams by writing a function which typically denoted by the letter pi, nothing to do with that 3.14 from the set 1 to 3 to 1 to 3. For example, pi of 1 is 3, pi of 2 is 1 and pi of 3 is 2. In fact, any such permutation will give rise to one way of selecting one entry from each row and each column. For instance, if I take this very simple permutation, 1 goes to 1, 2 goes to 2 and 3 goes to 3, then I get the first entry I will pick from row 1, column 1, that is this. The second one I will pick this, the third one I will pick this. That is a very simple case. Similarly, I could have picked these diagonal, in which case 1 would go to 3, 3 would go to 1 and 2 would remain in 2. Clearly, there are 3 factorial such permutations. So there are 3 factorial ways by which I can make my selections. And 3 factorial, that is 6. So there are 6 possible such ways by which I can do this. Now, the way determinants were originally defined, for each of these products, you will use one sign, either a plus sign or a minus sign. And that is where the trick comes in. To see how the sign is determined, I have taken this example. So 1 is going to 2. If 1 is going to 2, then row 1, column 2, I am picking this. 2 is going to 3, so I am taking this, and 3 is going to 1, so I am taking this. So the term that I get here is 4 times 5 times 3. Now I need to put either a plus 1 or minus 1 in front of it. The way I will determine it is by looking at this diagram and see how many times I have a crossing. I can see a crossing here, I have a crossing here. And if the number of crossing is even, as it is in this case, 2 is an even number, we will put a plus sign. So in this case, I shall put a plus sign. Had this number of crossing been an odd number, then we will put a minus sign. So we have got 3 factorial such things, each with its own sign. If I add up all these things, the number that I will get is called the determinant. A pretty magic definition. Just from the definition, you have no way of guessing why it is going to be useful or whether it is useful at all. So let us write down the definition of determinant clearly so that we can use it in our proof. I start with a square matrix n by n. I denote its ijth element by aij. Then I am going to find a magic number, call its determinant, and I do it in the following way. I first list all the rows 1 to n and all the columns 1 to n and take any permutation of them. So I take a bijection. Suppose I call this bijection pi. So this is a bijection which I will denote by the letter pi. In that case, this will govern how I pick the entries. For example, here I pick A1, 2. So in general, I will be picking A1 pi 1. Similarly, A2, 1, that is A2 pi 2. Going on like this, I will pick AN pi n. With this, I will add a sign, or not add a sign, multiply it with a sign. For that, I will count the number of crossings. I can see 1 crossing here, 2 crossings, 3 crossings, and there are more crossings in the dot dot part. So there is no straightforward way of writing it, so I will be just using a symbol. So epsilon pi will be what is called the sign of the permutation. It is plus 1 if the number of crossing is even and minus 1 if it is odd. So I will get how many such things? For each possible pi, I will get one such term, and there are exactly n factorial many such things. I will add it over all possible pi and define that to be the determinant. This definition is quite complicated as it stands, and if you have to compute determinant of some matrix using this is obviously a lot of work. So Leibniz, who originally came up with this definition, also thought about a way to compute it simply. Now, he did not publish it because he didn't think that determinants are going to be of any use in mathematics. Much later, Laplace rediscovered it, and that is why we call it Laplace expansion. So first we will see what it is using a simple example. Suppose I work with this 3 by 3 matrix and I want to compute its determinant directly from the definition. For this, first I have to list all the possible permutations of the numbers 1, 2 and 3. Each of these permutations will give rise to one such product term. So we have 6 such product terms. For all these things, the first indices are 1, 2, 3, 1, 2, 3, 1, 2, 3, but the blue things are dictated by these permutations. Then we have to decide about the signs. In the first case, 1, 2, 3 goes to 1, 2, 3, so there is no crossing. 0 is an even number. Remember, 0 is an even number, so I will get the sign plus. Similarly, for all the other permutations. Well, now Leibniz noticed that while this is quite complicated, and especially deciding about these signs, now let's just see this. In every term, we have each row and each column represented exactly 1. So I must be getting these first rows somewhere. So let's see where we get A11. So the terms where I get A11 are these and this. So if I take A11 common, then I will get A22, A33 minus A23, A32, which is precisely the determinant of this part. And similarly, if I look at wherever I get A12, in that case, these are the terms. And here, if I take that common, I will be getting the determinant made up of this and this. Similarly, if I take A13, I will get determinant of this part. So if I proceed in this way, then I am getting a formula by which I can express a 3 by 3 determinant as sum of 3 2 by 2 determinants. Now, as the order of the determinant goes down, it becomes easier to compute. So this formula is computationally useful, at least when you do the computation by hand. So by grouping the terms, I can write it as all the A11 terms will give you A11 times determinant of capital A11. I call this thing capital A11. Then once I take, say the last thing, A13, A13 gets multiplied with determinant of this thing, which I call capital A13. So basically, this capital Aij's are defined as you remove that particular element, the row and column of that, whatever submatrix remains. But however, there is something to be determined about the sign. It turns out that the sign here is plus 1, sign here is minus 1, and the sign here is plus 1 again. And Leibniz and later Laplace worked out a much simpler rule for determining these signs, and that is what leads to Laplace expansion. We start with a matrix n by n with ijth entry given by aij. Then Laplace expansion says that the determinant of A is you are expanding it along the first row. So with each element in the row, you multiply this thing. So whenever I have something called aij, suppose this is this element, this is my jth column, you strike out whatever is in the first row and the jth column, whatever remains, put them side by side, that matrix is called A1j. Compute its determinant. Notice that this is n minus 1 by n minus 1. So hopefully this is easier to compute than that one. Multiply it with the number A1j, then determine the sign in this rather simple way. You just take minus 1 to the power 1 plus j, 1 and j. You are adding them up. And in fact, you can generalize it further. There is no need to expand it only along the first row. You can expand it along any row. For example, about the ith row, just change these ones to i's. So you take any I in 1 to n, and then this will work. So this is Laplace expansion along the ith row. In fact, you can do it along some column. You can do Laplace expansion along the jth column, the same story, except that now you run your summation from I to 1 to n and keep j fixed. So that will be Laplace expansion along the jth column. Now we have already seen why this is a plausible formula. Basically, you are taking the entire formula of determinant, looking at all the terms that have aij's and extracting them. So whatever remains becomes the determinant of that together with this sign. So we are now going to prove that. Now the proof that we shall give will be from the first principles, and we have to show these three things. Number one, that there are exactly n factorial terms both here as well as there. We know that there are n factorial terms here. We have to argue that there are exactly n factorial terms here also. Secondly, we shall show that each term here has exactly one entry from each row and column. We know that each term here satisfies this condition. We shall show each term here also satisfies the same condition. And finally, we shall show that the signs match. Now, one is pretty obvious simply because, so we already know that there are exactly n factorial terms here. Now, once I expand this, so how many terms will be there? There will be exactly n minus 1 factorial terms. And so inside the ith sum, inside the ith term here, there will be n minus 1 factorial terms, and there are n such terms here. So the total number of terms on this side will be n times n minus 1 factorial, and as a result, there is exactly n factorial terms. And make sure that no term can be repeated, simply because inside each term nothing can be repeated, because all the n minus 1 factorial terms here are distinct by definition of determinant. And if you take one term from one value of I and another term from a different value of I, then this thing will be different because the value of I has changed. So all these n factorial terms here are distinct. So we indeed have n factorial terms here. We already know we have n factorial terms there. In order to see why the second condition will hold, let's look at the diagram. So when I consider determinant of aij, every term here will avoid the ith row and the jth column, because I have got aij by deleting those two rows and columns. So every term will be by a bijection of the remaining things. So possibly 1 goes to 2, 2 goes to n, this goes to here, that goes to there, and things like that. So all the other things other than I will have an arrow coming out of it, and all the numbers here except j will have an arrow coming into it. So we know that all the other rows and columns have been represented, that is, there is exactly one entry from them. only the ith row and the jth column are left out. Now when I multiply it with aij, I am supplying that column. I am supplying that term, so both the ith row and the jth column gets represented. As a result, each term, each of those n factorial terms has exactly one entry from each row and each column. So these two things could be proved just by observing. Some difficulty will arise in proving that the signs match, and that is precisely where Laplace expansion becomes useful, because here the computation of the signs is pretty trivial, whereas the computation of sign here was pretty complicated. To prove that signs match, we have to proceed carefully, and this is the core of this proof. Remember, whenever we are considering any term here, this already comes with its sign, because there is the number of crossing in the arrows that we already use here. And there are a number of crossings that we get here. My contention is, when we put this aij term, the extra contribution to the sign is exactly -1 to the power I plus j. So clearly understand what I am going to show. I already have an arrow diagram that lifts out I and lifts out j. There are arrows coming out of everything other than I and arrows going into everything other than j. That itself has a number of crossings determining the sign of the term inside determinant ij. Now I add an arrow from I to j. As a result, the number of crossings change because this arrow will cross some of the other arrows. I claim that as a result, the change in the number of crossings, which will contribute to the change in sign, is exactly this. Why is that? Let's see. Suppose I consider the arrows that I already have. So I have all the arrows coming from here. Now I will consider this particular arrow. So this arrow will intersect some of the existing arrows. Now what are the existing arrows? So some of the arrows will crossing like this, and some of the arrows will be crossing like this. I have to count all those new crossings that result from giving the ij thing. I do not know how many of these are there, so let's say there are k such arrows that come here. So each contributes one crossing, so the number of crossings go up by k. Now how many gaps are there? We are not using j here, so there are exactly n minus j places where these arrows can go. So how many things are now left out? The number of things that are left out unused is bound to be n minus j minus k. So k arrows contribute k crossings, and these are here. How many things are here? I have I minus n many points here. Of these n minus j minus k things are clearly filled up, because for these points the arrow cannot come from above, because if that is the case, then I would count them already as coming down. So these arrows must be filled up by things here. So all these n minus j minus k things must be filled up by arrows that come from under I. If that is the case, how many are left out? I had I minus n many arrows below I, of which n minus j minus k have been accounted for. They are not crossing this arrow. So if you just do the computation, you will see it is I plus j minus 2n minus k. So clearly these many arrows have to go up because they do not have space here. So those things will go up and contribute further to my number of crossings. So I already had k crossings. Now with it I add this many. So with it I add I plus j minus 2n minus k, which means the total number of crossings that I get is, cancel this k and k, I plus j minus 2n. Now remember, I care only about the parity of the number of crossings, that is whether it is even or odd. 2n is not going to contribute to that because it's an even number. If you add or subtract an even number from something, the parity remains unchanged. Odd remains odd, even remains even. So I can safely forget about that. So the number of extra crossings that you have, the parity of it, is determined completely by just I and j using the simple formula. And that is precisely what I have written. The only extra contribution will be minus 1 to the power I plus j, and that finishes the proof of Laplace expansion.